Okay, sorry about that, guys. I forgot to delete some videos on my camera, so it stopped recording because it ran out of space. You think I would be a pro at this by now, right? All the videos I've made, but still working on it. All right, so let's go back to what we were talking about before. So here, I want to be able to kind of extend this idea of the Taylor series of one variable to two variables, right? So we have our f of x, y. Now we want to deal with our first derivative terms, right? And since we have two variables, right, we're going to have a first derivatives in terms of x and y, so we get partial derivatives in this case, right? So let's deal with the partial derivative of f with respect to x first. So we have plus the partial derivative of f with respect to x comma y, times, here we have an h, right? The h corresponds with being added to the x that we have here, right? What's being added to the x here is an ah, so we're going to have times ah plus. Now let's deal with the partial derivative of f with respect to y, our second variable. So partial derivative of f with respect to y, x comma y. And what's being added to the y is a bh, so we're going to have times bh plus. Now we need to deal with our partial derivative, our second derivative, right, extension, right? So we have to deal with our second order partial derivatives, right? That's what happens now. So we're going to the second derivative now, so the second order partial derivatives. So the partial derivative of f with respect to x, then x again. The partial derivative of f with respect to x and y. The partial derivative with respect to y, then x. And then the partial derivative with respect to y, and then y again, right? So that's going to deal with our second order. And guess what? We're going to stop after that. We don't want to go any further than that. That's a little bit too much for us already, right? Like, my goodness, how big is this going to be? So let's keep writing. So the partial derivative of f with respect to x, then x again, x comma y. Note that we have an h squared here, right? And that h squared is coming from, because it's going to be, we're squaring everything, so it's going to be ah squared. AH squared, because the AH is being added to the x, so think about a AH from the first x and an AH from the second x. So AH times AH gives us AH squared, plus the partial derivative of f with respect to y, then y. Let's do that one first. X comma y. I'm going to get a BH squared plus, oh, you know what I'm forgetting? I'm forgetting what? I'm forgetting a 2 factorial, right? So let's do that here. So I need to multiply this thing by, divided by 2 factorial here, right? And a 2 factorial here. Forgot about my factorials, can't forget about that. Right, just like we have a 2 factorial here, we're going to have a 2 factorial for both of these guys. Plus, now let's deal with our other guys. Partial derivative of f with respect to x, then y, x comma y, divided by 2 factorial. And we're going to get a ah from the x and a bh from the y. Okay. And likewise, when we do the partial derivative of f with respect to y, then x, that's going to be our last one. You're like, oh my goodness, Dr. West, this is already quite a bit. And yes, it is. H, BH, over 2 factorial, plus da da da. It keeps on going, right? This is a lot to put down. So a lot of times what you'll see people do, right, to kind of make this a little bit less hairy, is they won't write the x comma y every single time. So they'll do this. And that's what we're going to do too. I have f of x plus h, comma y plus bh. I'm really going to write it like this. I'm going to have f plus the partial derivative of f with respect to x times ah plus the partial derivative of f with respect to y times bh plus the partial derivative of f with respect to x and x times h squared plus f y bh squared plus, oh, divided by 2 factorial. Thank you, guys. And then I have x comma y, ah bh over 2 factorial plus y then x ah bh 2 factorial. Now usually you guys already know from calculus 3 that these two guys should be equal to each other, right? As long as f is continuous in terms of its partial derivatives. We can make that assertion. I'm not going to do that here. I'm going to just keep them separate. But usually these two guys, these two terms are exactly the same, so you can actually combine them together into one term. Again, I'm not going to do that here. I'm just going to stop there. And lo and behold, this Taylor series goes on much longer than this, right? This can extend out to the third derivative, right? The fourth derivative, the fifth derivative. It goes on forever, right? Because this is a Taylor series. Okay, so I think I wrote that down correctly. Let's do an example. It's enough just to write all this stuff down, but let's look at an example. Notice that how many terms do I have here? I have 1, 2, 3, 4, 5, 6, 7 terms here. So let's look at an example. And let's just write down the first 7 terms of the Taylor series. So I'm going to say write the first 7 terms of the Taylor series of, here I have f of x plus 2h, I believe, y, comma, y plus 3h, for f of x, y equal to, I have e to the x, y. E to the x, y. So I'm going to write the first 7 terms of the Taylor series, first 7 terms of the Taylor series of f of x plus 2h, y plus 3h, for f of x, y equal to e to the x, y. All right. If I could talk today, right, it's going to be one of those days, I think. All right. So what we want to do is we need to find the first order partials and the second order partials, right? Once we do that, we're going to add them all together using this form that we have here. And then that'll be our Taylor series, at least the first 7 terms of the Taylor series. So let's do that. I need to find these partial derivatives. y here. And I have x comma y. Do I have enough space? Let me move it over a little bit. Okay. Let's move this guy over. All right. Good enough. You guys can do this using your calculator if you like. The partial derivative of f with respect to x, I think is going to be y, e to the xy. Okay. The partial derivative of f with respect to y, I think is going to be x, e to the xy. The partial derivative of f with respect to x and x again, I believe it's going to be, what do we have here? This is going to, no, I don't have the chain rule here. It should be just y squared. Yep. E to the xy. The partial derivative of f with respect to y, and then y again, I believe it's going to be x squared. E to the xy. You guys can check this out, make sure that I did this correctly. And then the partial derivative of f with respect to x, then y, I have xy, e to the xy. xy, e to the xy. And let's make sure that's correct. Make sure we did that right. And the y. Okay. Doing this on the camera here. So we have y, e to the xy, y. And what do we have here when we do this? The derivative of the first is going to be 1 times e to the xy plus the derivative of the second is going to be with respect to y is going to be x, y, e to xy. So I did that wrong. So this should be e to xy plus xy, e to xy. So we're going to have xy plus times e to xy plus e to xy. Okay. I believe that is correct. I did that right. All right. I'm going to erase this. I think I'm good here. Yep. I'm going to erase this here. Now let's keep going. Let's do our Taylor series here. So we have F, you see it, all this on camera, right? So A is equal to 2, and then B is equal to 3, right? So let's plug it in. So we have F of x plus 2h, y plus 3h is equal to, I have F, which is e to the xy, plus the partial derivative of f with respect to x is going to be y, e to the xy, times ah, which is going to be, in this case, 2h, plus the partial derivative of f with respect to y is x, e to the xy, times 3h, plus the partial derivative of f with respect to x, and x again, we saw that that was y squared, e to the xy, times 2h squared divided by 2 factorial. Plus, here we have the partial derivative of f with respect to y, then y again, we have x squared, e to the xy, times 3h squared over 2 factorial. Plus, okay, the partial derivative of f with respect to x and y, so I have xy, e to xy, plus e to xy, divided by 2 factorial. All that times ah times bh. ah times bh, which is going to be 2h times 3h, which is going to be 6h squared. Just write 6h squared, save space. Plus the partial derivative of f with respect to y, then x. And again, we could check to make sure that these guys are equal, right? Partial derivative with respect to y, then x. I'll put it over here. X, we already saw that that was x, e to the xy, x again. So the derivative of the first will be 1 times the second, plus the derivative of the second, right, e to xy is going to be y, e to xy, so I get xy, e to xy, which is the same thing we have over there. So I get xy, e to xy, plus e to xy, divided by 2 factorial, times ah plus bh, which is going to give us 6h squared. Again. Okay. So this is our Taylor series with the first 7 terms. Right. And what we could do is, now that we have this, we can plug in a value, plug in a point. And I'll erase this right here. For this type of thing, you don't have enough space, right? There's not enough space in the world. But I can get rid of this, and I'll keep this one. I'll keep this one here so you guys can see it. Not enough space in the world for all this stuff. Now, if I wanted to, I could say, well, a Taylor approximation just using the first 7 points. Let's say where x is equal to 1. Let's say x is equal to, let's say 0. X is equal to 1. Y is equal to 1. H equal to 0.1. Okay. You can do that. Then if we plug in, we have f of x plus 2h, y plus 3h, right? If you guys look at that, we know that's really f of x is 1, h is 0.1, so this is 1.2, comma, then this is going to be 1.3 for the second part. And I could say that whatever my function value, remember that f of xy is equal to e to xy, right? So I can approximate this function at 1.2, 1.3 using my Taylor series that I just have over there by just plugging in 1 for x, 1 for y, and h equal to 0.1. So if I do that here, and I'll let you guys see if these are equal to each, are approximately equal to each other. This becomes e to the 1. Here I'm plugging in x being 1 and y being 1 into this Taylor series. So I'm going to say this is approximately equal to, okay, plus 1 times e to the 1, 2h, which is going to be 0.2, plus, this becomes 1 times e to the 1, times 3h, which is 0.3, plus, this term becomes 1 squared, which is 1, times e to the 1, right? Divided by 2 times 0.2 squared. So this becomes e to the 1. 0.2 squared divided by 2. Okay. Plus, I got to squeeze one more term in here. This becomes e to the 1. 0.3 squared divided by 2 factorial, which is what we have here, plus, it's long, right? Plus, what do we have here? This is our next one, right, which is going to be 1 times e to the 1 plus e to the 1 divided by 2, and we get 6 times h squared. Oh, h squared. So 0.1 squared is 0.01, I believe. So this is 0.06, I believe. And then we get the same thing again. All right, so let's just look at that. Marvel at that beauty that we have there. Right. Okay. Now, if I did this correctly, which I think I did, I feel good about it. What I get, if I did it correctly, is 4.593896, Okay. If I didn't make any mistakes, okay, if I didn't make any mistakes. And did I make a mistake? I'm gonna double check it after I finish this. If I didn't make a mistake, I'll let you know. And then my actual value, numerical analysis. You always should double check your work. Double check your work over and over again. I should have double checked this again. My actual, when I did this, f of 1.2 comma 1.3, which is e to the 1.2 times 1.3, I got that to be equal to 4.7 588212. So I'll double check both of those guys and see if I get the same thing. I definitely want to double check this one again to make sure that everything's okay. All right, but that's the Taylor approximation of e to the x, y. And I know it looks complicated, but most of our Taylor approximations do look complicated, but they can be very useful later on, especially when we're dealing with, we want to be able to come up with a polynomial approximation, things like that. So Taylor series are very useful there. But also Taylor series are very useful when we want to be able to come up and derive particular formulas or methods, right? Like we did with derivatives and what we did with integrals. And we're going to do the same thing with Runge-Kutta. Before we kind of go on to the next topic, right? And again, I'll double check this and I'll let you guys know if there's any error. But before we go to the next topic, let's just do one more example. Another example. So I want to write the first 7 terms of the Taylor series, and I'm going to pick a different function about a different couple of numbers, right? That's what we're going to do. So I want to be able to write the first 7 terms of the Taylor series of f of x plus, let's say, 5h, f of x plus 5h, and here I have y minus 2h. I have y minus 2h. I would say I need more coffee, but it's actually around 5 o'clock here. For f of x, y equal to, not in the morning, but in the evening, f of x, y is equal to 5x cubed times y to the 4th. Okay. So let's just do one more example because I'm going to have you guys do some of these in your homework, so I want to make sure that you know how to do it. So a couple examples in your notes so you can have it. Okay, let's look at this. So I want to write the first 7 terms of the Taylor series of f of x plus 5h, y minus 2h for f of x, y equal to 5x cubed, y to the 4th times y to the 4th. Right? So again, the first thing we need to do